Hello guys, welcome once more to another video in our YouTube channel. So in this video we are going to divert to physics and we are going to be looking at advanced level physics paper 2 of June 2023, specifically section A, and we are going to be answering all the questions. So before we get started, I would like you to take a piece of paper or a jotting material, your pen and your calculator. Is very important because I am not going to be punching for you. I'll basically be analyzing equations, bringing out the general formula, giving you the constants and giving you the final answer for you to punch. So along the way, if you have any difficulty, you make sure you indicate in the comment section so that your difficulty will be addressed. All right, so let's get started. In fact, for those of you who are just joining us, okay, make sure you like the video, you share the video with your friends, you subscribe to the channel. Importantly, turn on your notifications so that whenever we upload subsequent videos, you always be the first to be notified to come and watch. Make sure you share the video with your friends after watching. It's very important. That's going to motivate us. Make sure you comment if the video is good and if you need more videos of such. So without wasting much of your time, let's dive straight away into the solution of Physics 2023 Paper 2, Section A. Alright, so we move directly to the first question. This section contains 5 questions, and in this video we are solving all the 5 questions briefly. So in every slide I'm going to display the question to you, and then we are going to look at the solution together after analyzing. So the question reads: A. Explain what makes an equation relating physical quantities to be homogeneous, to be physically correct. So we are going to begin with the A part first. Okay, so what makes an equation relating physical quantities to be homogeneous? Basically, a homogeneous equation is which type of equation? Is basically one in which the dimensions or the base unit of every term is the same. Okay, or you can say the base units of the additive terms in all the sides are the same. So if the base units of every term in an equation or the dimensions of every term are all the same, then that equation is said to be homogeneous. So that's the answer to Roman 1. Now, what makes an equation to be physically correct? A physically correct equation is basically an equation in which, first of all, it is homogeneous, and secondly, it possesses the correct dimensionless or unitless constants. Alright, so once an equation is firstly homogeneous and possesses the correct dimensionless or unitless constants, then it is physically correct. For example, if I say f is equal to 2ma, you realize that that equation is homogeneous, but it is not physically correct because we know that f is equal to ma. But when we're adding 2 to it, 2 is basically a dimensionless constant, but it is not the correct dimensionless constant for the equation relating the mass and the acceleration, because we know f equal to ma means that f equal to 1 ma. So the correct dimensionless constant there is 1. But if we say f is equal to 2ma, then it's going to be homogeneous, okay, because the base units on either side of the equation are going to be equal. But now, because the 2 is there, which is not the correct dimensionless constant, then that equation will not be physically correct. So for an equation to be physically correct, these two properties must be together. Alright, now the B part says the thermometric EMF E generated in a thermocouple when a cold junction is placed in contact with ice and the hot junction placed in a bowl of water at a temperature theta is given by this equation. So this equation is relating the EMF and the temperature. Now E0 is the EMF when theta is equal to 0 degrees and alpha and beta are constants. The above equation is homogeneous. Clear. Determine the base units of Roman 1 alpha theta and beta theta squared, and Roman 2 alpha and beta. So how do I get the base units of alpha theta and beta theta squared? The explanation has already been given to you. Now you realize that this equation is E equal to E0 times a certain something 1 plus alpha theta plus beta theta squared, and so on and so forth. Now you clearly see that since E E0 is also EMF. Okay, it therefore means that an E as well is also EMF. Then for this equation to be homogeneous, then 1 plus theta 1, in fact this quantity in bracket is supposed to be unitless. Okay, all right, because if this quantity in bracket has base units, then it therefore means that this equation will not be homogeneous, because you already see that E is equal to E0. So the base units of this quantity in bracket should give you the base units of E divided by the base units of E0. But the base units of E and E0 are the same. It therefore means that the base units of this, it means that if they are the same, then they are going to cancel off. So the base units of this quantity in bracket is just in fact he has no base units, since the base units of E and E0 will cancel off. So the quantity in bracket here is supposed to be unitless. All right, and since this one here, okay, is unitless, it therefore means that alpha theta, beta theta squared, and all the quantities are independently supposed to be unitless. Okay, so that's why I said that since we are adding alpha theta and beta theta squared to a unitless constant, which is 1, it therefore means that alpha theta and beta theta squared are independently supposed to be also unitless. So they have no base units, so they are unitless. Now for the second part, you clearly see that for you to get the base units of alpha, if alpha theta is unitless, it means that it is actually equal to a constant, because only constants are unitless. Now that's basically constants are unitless. If beta theta squared is also unitless, it means that it is also equal to a constant, since constants are unitless. Now if alpha theta is equal to a constant, then clearly the base units of alpha will be 1 divided by the base units of theta, since the base units of this constant n here is basically in fact this n is unitless. All right, so when we are dealing with the base units of alpha will be 1 divided by the base units of beta. Alpha theta equal to n is a homogeneous equation. Okay, but it is not physically correct, because this n here might not be the correct dimensionless constant or the correct unitless constant to be used. But since it is homogeneous, it therefore means that the base units of, in fact you're going to have that alpha is equal to n over theta. Since n is unitless, it means that the base units of alpha will be 1 over the base unit of theta, and theta is temperature, so the base unit is a Kelvin, so we have 1 over the Kelvin, which is a per Kelvin. What about the base unit of beta? It will just give you 1 over the base units of theta squared, which is Kelvin to the minus 2, or per Kelvin squared. All right, so we are done with the first question. Do well to comment in the comment section if you feel like there is any problem anywhere, or if you've not understood, or if the solution is perfectly explained. Let's go directly to the second question. Alright, so question 2 is on thermodynamics, and it reads: the volume of a gas changes from this to this as it expands adiabatically against the atmosphere, which exerts a pressure of this. A. Calculate the work done by the gas. So let's begin with the A part. How do we calculate the work done by the gas? So the work done by the gas is just the pressure times the change in volume, since the gas is expanding. Alright, so the pressure has been given to us. What about the change in volume? Is a final volume minus the initial volume. So the change in volume is a final volume minus the initial volume. When you subtract, you're going to get your answer. So make sure you punch your calculator, because in this step I'm not going to be solving, I'm not going to be punching for you. I'm not going to be doing all the manipulations for you. I've already punched, and I'll just be giving you the answers so that we move faster. So the change in volume is equal to the final volume minus the initial volume, and the unit is meters cubed. So, and the pressure has been given as 1.10 times 10 to the power 5 Pascal. So the work done is basically 3.52 times 10 raised to the power 2 joules. So when you get your change in volume, you multiply by the you basically multiply by you multiply by this. Okay, you multiply by the pressure, then you get your answers in joules directly. All right, so let's move on to the B part of the question, which is asking us to state and explain how the temperature of the gas changes in the process. So basically we have that the heat supplied to the system is its internal energy plus the work done the work done by the gas on the system. So since the gas is expanding adiabatically, then the net heat is equal to 0. All right, so from there now we get that if delta Q is 0, then delta U will give you minus W. So it therefore means that the change in internal energy will be negative. Why will it be negative? Because the work done has been calculated and it is positive. Okay, it therefore means that since work done is positive, if I multiply both sides by negative, negative work done will be less than 0. But the negative work done gives you the change in internal energy, which means that the change in internal energy will be less than 0. And the change in internal energy is basically the final internal energy minus the initial internal energy. If the final minus the initial is less than 0, it therefore means that the final is less than the initial. If the final is less than the initial, it means that there's a decrease in internal energy, because the final value is smaller than the initial value. And when there's a decrease in internal energy, it means that there's a decrease in temperature, because those two things are directly proportional. Now you have to recall that the internal energy of a system can be thought of as the sum of all kinetic energies of the individual gas molecules, and you can also relate kinetic energy with temperature. They also have a direct relationship. And lastly, an increase in the temperature increases the kinetic energy, hence also increases the internal energy, since the internal energy can be thought of as a sum of all the kinetic energies of the system. All right, the last part of the equation is asking us to name one practical situation in which this change can be experienced. That is, which change? A gas changes in the volume of a gas changes as it expands adiabatically against the atmosphere, which exerts a certain pressure. So I'm going to give you some practical situations. I'm not just going to give you one, I'm going to give you like 3 of them or 4 of them, so that you clearly see where this can be applied practically. So the first practical situation is cloud formation in the atmosphere. When clouds are being formed, the volume of gases change in volume. That's the gases change in volume, and basically since they are formed in the atmosphere, then the atmosphere will basically exert a certain pressure on the gas, okay, and it's going to expand adiabatically. The second one is spraying perfume into the atmosphere. When you spray perfume into the atmosphere, this process occurs. And lastly is a rapid escape of gas from a burst balloon. So if maybe you fill a balloon with air and then you burst it, you realize that gas is going to be escaping this balloon because you have burst it, and this process is going to occur again. So that's it for the second question. So let's move directly to the third question. Alright, so the third question we have: in the process of producing lasers, atoms of the active medium are excited from the ground state, which is n equal to 1. I've given you the energy, the value of the energy level, to n equal to 3, and I've given you the value of the energy level. These atoms then fall back momentarily to another energy level, n equal to 2. I've given you the value of the energy at that level. They are then stimulated by a suitable energy photon to fall back to n equal to 1 level. A. Define the following words and expressions as used in relation to lasers: optical pumping, population inversion. B. Explain why the laser beam has a high intensity and calculate the wavelength of the light produced. You see this red thing here is basically a laser. Okay, so this is what you see here is a laser. So what is optical pumping? I'm just going to give you the definition. So optical pumping basically involves taking atoms from the ground state to an excited state with the help of light. That is optical pumping. What about population inversion? So this is a condition where there are more atoms in a higher excited state than in the lower preceding state. That is population inversion. All right, now let's go to B, which is asking us to calculate, or maybe to first of all explain why the laser beam has a high intensity, and we calculate the wavelength of the light produced. So your first assignment is to tell me in the comment section what the acronym laser means, because laser stands for something. It's an acronym, that's why you see it in capital letter. All right, so you need to tell me what it means. Laser, it has a full meaning. Let me start. Light amplification. I think you're going to complete it. Tell me in the comment section if you know what it means. So now, why is it that the laser beam has a high intensity? Basically, a laser beam is narrow, it is highly concentrated in a particular direction, so all the energy is confined within one small space. Okay, you can think about, maybe those of you who watch action movies, you usually see, maybe, I don't know if it is maybe a military guy or a bandit holds a certain gun that has a certain red light, which if that red light passes through maybe a certain surface, the surface divides. So we can always use lasers to cut metals and to deform shapes and so on and so forth. All right, so it is very narrow and highly concentrated in a particular direction, so all the energy is confined within a small space region. So that's why it has a high intensity. Now, how do we get the wavelength? The wavelength of the light produced. Let's get back to the equation. The equation says that these atoms then fall back momentarily to n equal to 2. So they first of all moved from an excited state. They first of all moved from the ground state to an excited state, that is optical pumping. And then what happens again? What happens is that they now fall back to n equal to 2, and then a certain photon, because they are then stimulated by a suitable energy photon, and they fall back to the ground. So it basically means that the only two energy levels we are going to be using here is E equal to 2 and E equal to 1. All right, because the photon came when it was at energy level n equal to 2, and then sent it back to the ground state, which is the energy level n equal to 1. You can see relationship between the given paragraph here and optical pumping as well as population inversion. All right, so basically we have that the energy of a photon, first of all, let's relate the energy and the frequency as well as the Planck's constant. So the energy is hf, where h is a Planck's constant and f is the frequency, and we know that v is equal to f lambda, okay, where v here is the speed of light, your f is a frequency, and lambda is the wavelength of that light. So we clearly have that your f becomes v over lambda. If you replace f with v over lambda, we get that the energy of that photon is hv over lambda. Your v is basically the speed of light, h is the Planck's constant, and the lambda is the wavelength of that light. So it therefore means that if we want to find lambda, we need to multiply by lambda, and then we divide by the energy. So lambda becomes hv divided by E. Now what is E? It is basically the change in energy, which is, since the photon came when that atom was in energy level where n is equal to 2, and it took it back to the energy level where n is equal to 1, that is the ground state. It therefore means that the energy involved is the energy involved in only that process. We are not concerned with n equal to 3 again, okay, because the photon was coming when the atom was already at n equal to 2 after falling back. All right, so the change in energy is E2 minus E1, because it was moving from E2 from n equal to 2 to n equal to 1. So n equal to 2 is a little bit higher than n equal to 1. So we have E to be equal to E2 minus E1. H is a Planck's constant, like I said, okay. V is the speed of light in air. We know the value is 3 times 10 raised to the power 8 meters per second. Now that energy becomes E equal to 2 was given as negative 5.8 electron volts. E equal to 1 was given as negative 11.2 electron volts. So when we take negative 5.8 minus negative 11.2, the result is going to be in electron volts. You will get your answer in electron volts, but now we have to do the conversion. 1 electron volt in terms of energy is 1.6 times 10 to the negative 19 joules. Okay, the speed of light in air is 3.0 times 10 raised to the power 8 meters per second, and the Planck's constant is 6.63 times 10 raised to the power negative 34 joules second. So from there, since we need the wavelength, we just need to replace h, that is the Planck's constant, with its value, we replace V with the speed of light in air, then we divide by the energy, where we are going to multiply the answer we have here after doing the arithmetic with the with 1 electron volt in terms of energy. So the answer here is going to be in terms of electron volt. We need to convert it to joules. So if 1 electron volt is equal to this, it means that this energy, which is in electron volt, will give you what value. You do the simple proportion and you get the energy in joules. All right, and then you replace it in the formula. Once you do that correctly, you're going to have your wavelength as 2.31 times 10 to the negative 7 meters. So like I said, do well to be with your calculator so that you punch directly and have your answer, so you know that you're done with the question. All right, let's move on to the next question. Okay, so question number 4, it is a question which was a little bit technical, all right, but though not so technical, but it was unusual, because most of the times you usually just see a spring, a spring and a mass, just one spring and a mass, but here you have two springs. A 0.8 kilogram mass is hanging from a helical spring. It produces an extension of 5.2 centimeters in it. Now, the object is then suspended from two such springs as shown in the figure 1. This is figure 1. If the mass is then pulled down through a further distance of 4.8 centimeters and allowed to oscillate freely in a vertical plane, so you pull it down, like you pull it down, and then now it is oscillating because the springs are elastic, so it is oscillating. A, determine the period of oscillation of the mass. So the period, first of all, since it is a mass spring system, then the period is given by 2 pi the square root of m on k, where m is a mass of the object and k is a spring's constant. Now this k is basically the sum of the spring constants of the two springs, but the two springs are the same. Okay, that's because they say two such springs. So when they say two such springs, it means that they are the same, so it is not an assumption. So let's say that the spring constants of the original springs are k0 and k0. It therefore means that your k is a sum of their spring constants, which gives you 2k0. Now we need to find the value of k0. Okay, so initially when it was just connected to one spring, we had the force, the weight of the, when it was pulled down, okay, the weight is mg, and then the force, there's a resisting force, which is a tension in the string, is acting towards the fixed support. So according to Hooke's law, that force is equal to, according to Newton's law, that force is mg, and according to Hooke's law, that force is the spring constant times the extension. If you state Hooke's law, the force is always proportional to the extension, okay, and the constant of proportionality is a spring constant. So from here, it therefore means that our k0, so this follows Hooke's law that F is equal to k0e, but F is also equal to mg to balance the forces in the vertical direction. So it therefore means that my k0 is equal to mg divided by e, where e is the original extension. In fact, it's anyways, you are going to see what e is. All right, so k0 is mg divided by e, where m is a mass, g is the acceleration due to gravity, and e is the extension. All right, so from there we get our k, which was 2k0, becomes, I just multiply mg on e by 2, we get 2mg divided by e. Now what about m divided by k? If I divide both sides by k, okay, I'm going to have, and I multiply by e and I divide by g, I'm basically going to have that m divided by k should give me, I think it's e divided by 2g. There's a little mistake on my side, so this 2 is supposed to be in the denominator, so it's not supposed to be here. Okay, it's supposed to be rather in the denominator, because it's supposed to be multiplying the g. Okay, all right, now from there what do we have? We have that, like I said, guys, this 2 is supposed to be in the denominator, not in the numerator. So it's supposed to be e divided by 2g. Okay, your G is 9.8. Now let us have the values. Your E is the original extension, okay, because that E is not the extension of 4.8. No, it is the extension of 5.2, because that E is as a result of the Hooke's law when we're applying in just a single string. K0 times E is that extension. So I've changed it to meters. We divide by 100. What about G? 9.8 meters per second squared. So when you punch correctly, I'm going to give you the answer at the end. Now let's go to the second part of the equation. How do I now sketch a graph showing how the mechanical energy of the mass varies with displacement from the rest position? Now this displacement is a vertical displacement since it was oscillating in a vertical plane. So I have a graph where I am plotting mechanical energy against the vertical displacement. My mechanical energy, the unit is joules. My vertical displacement, the unit is meters. So you clearly see that the maximum displacement and the minimum displacement, since it was pulled down, okay, it was pulled down through a further distance of 4.8, it means that the maximum displacement is 0.48 since I'm dealing with meters. So the maximum displacement is 0.48. So when it's pulled down, it goes back up. Okay, so the minimum displacement, when you're going down, my reference frame says when you go down, you are positive. When you go up, you are negative. So once you are going down, you are traveling a vertical distance downwards, you are positive according to my reference frame. Okay, so when you are going down, you are positive. So when you are traveling the distance downwards, it is positive 0.48. Now the minimum that you are going to take is now the 0.48 but in the reversed direction. So that's why I have negative 0.48. So the kinetic energy, let's begin with the potential energy. Because mechanical energy is kinetic energy plus potential energy. So we are going to draw the two graphs. For potential energy, we have this graph where potential energy is 0 at the equilibrium position when no distance is traveled. Now as you travel downwards, when you travel vertical distances pointing downward, we have this shape, and when you travel vertical distances back upwards, we now have this shape. Because when you're going downwards, you are positive, and when you're going down, when you're going downwards, you are positive since you're traveling in the direction of motion, and when you're going upwards, you are negative according to my reference frame. Somebody can also choose a different reference frame. Okay, now what about the potential, the kinetic energy? Rather, the kinetic energy will instead, so that's potential energy. So kinetic energy will be 0 when you have traveled your maximum or your minimum displacement. So when you have traveled the maximum, when you have traveled through the maximum distance, your kinetic energy is 0, and your kinetic energy is maximum at the equilibrium position. All right, so that is why we have this is the maximum value of the kinetic energy, and then the sum, that's kinetic energy, the sum of the two gives you the mechanical energy. So this is a graph that relates mechanical energy and the vertical displacement from the equilibrium position of the mass. Like I said, I'm going to give you the final answer of that tension, 0.23 seconds. So when you punch, remember I said the 2 is supposed to be in the denominator. Okay, so once you punch, you're going to have 0.23 seconds. So make sure you punch and you tell me in your comments, in the comment section, if that is also your response. Let's go to the last question, which is question 5. All right, so this is an equation on current electricity, maybe linked a little bit with electric fields, capacitors. It reads, some electrical components are connected together in a circuit energized by a 3.00 volt battery as shown in this figure. So we have this. The capacitors are initially uncharged. The contact point Z of the switch is closed at the point X unit. The 100 microfarad capacitor is fully charged. When Z is now moved to contact with Y, determine the initial current in the circuit, the maximum charge that will be stored in the 150 microfarad capacitor. So let's begin with the initial current. So basically initially you know that V is equal to I arrow, where V is a voltage of the circuit, I is a current of the circuit, and then R is a resistance of the circuit. Alright, so initially we have that 150 and 100 microfarad capacitors were uncharged. Alright, so V equal to I arrow means that I equal to V on arrow. Your V is basically 3 and your arrow is 1.5 kilo ohms. Kilo is 10 raised to the power 3. So when you do volts divided by ohms, give you amperes. So when you simplify, you get your answer as 2 times 10 to the negative 3 amperes. That's the value of the initial current. Now, how do I get the maximum charge that will be stored in the 150 microfarad capacitor? So I first of all start by getting the charge in the initial, that's the charge in the initial state of the system, that's the initial charge. I can call it Cure I, or I can call it Cure. So we know that Cure is basically equal to CV, okay, where C is a capacitance of the system, that's the resultant, the effective capacitance, that's the right word to use, the effective capacitance, and V is the supplied voltage. So initially you realize that because the equation says that when Z is now moved to make a contact with Y, it means that Z was not initially with Y. So it means that initially we just had this 150 microfarad capacitor was not involved in the system. We just had this little part down. In fact, this switch here was open, so current was not, the voltage was not going through this way, the current was not going through this way, so this empty space was there. All right, so so the capacitance, the effective capacitance of the circuit initially is basically the 100 microfarad. Is basically the capacitance of the 100 microfarad capacitor, which is 100 microfarads, okay, and the voltage is 3 volts. That's in the initial state. It's now in the final stage where the 150 microfarad capacitor was now introduced, which we need now to find the charge of the charge that will be stored in the 150 microfarad capacitor. Remember, a capacitor is basically a device that stores charge. All right, so when Z is now connected to Y, then since current is flowing, it means that this capacitor here will store charge. Okay, all right, so initially Q is equal to CV. We know C is basically the initial capacitance, which is 100 microfarad. Micro is 10 to the minus 6, and V is the initial voltage, which is 3, and the unit for charge is coulombs. This C here is coulombs. So when we simplify, we get 3 times 10 to the negative 4 coulombs. That is the initial charge. Now we can now use the principle of conservation of charge, which says that the initial charge is equal to the final charge. Okay, and the final charge is basically summing the charge stored by the 100 farad capacitor, which is, I'm just going to call that this 100 farad capacitor is A, and the 150 microfarad capacitor is B. So the final charge of the circuit is the sum of the charges stored by the 100 microfarad and the 150 microfarad capacitors. And from the conservation of charge, the initial charge of the system must be equal to the final charge. All right, charge it cannot be lost, it is always conserved. That's the principle of conservation of charge. So from here, what do we have? We have that if we add the charges stored by those two capacitors, it must give us the initial charge, which is Q, since summing those charges is the final charge, and from the principle, the final charge is equal to the initial charge. Now we have already calculated the value of the initial charge, which is 3 times 10 to the negative 4 coulombs. Now, since the voltage across the 100 microfarad is the same as the voltage across the 150 microfarad, since Z will now be in contact with Y, it therefore means that voltage, if Q is equal to CV, it means V will be equal to Q on C. So VA is the voltage across the 100 microfarad, which is QA on CA, that is the charge it stores divided by its capacitance. Same thing for the voltage across the 150 microfarad capacitor. So this means that if I cross multiply, I have cure A CB equal to cure B CA, or we just say cure B CA equal to cure A CB. Now we have two equations with two unknowns, and we can find the two unknowns. In fact, we just need one unknown, which is cure B, since we are looking for the charge that will be stored in the 150 microfarad capacitor. So from here we just replace our cure A. If we come to this first equation, we realize that cure A is cure minus cure B. We have the value of cure, and since we are finding cure B, if we expand the right hand side, we have cure times CB minus cure B times CB. We make cure B the subject of the formula by adding this quantity on both sides and then dividing both sides by its coefficient. We get cure B to be cure CB over CA plus CB. Your cure, we calculated cure already, is 3 times 10 to the negative 4 coulombs. What about CB? Is a capacitance of the capacitor B, which is 150 microfarad. What about CA? CA is what? The capacitance of capacitor A, which is 100 microfarad. So pay keen attention to the units, and when you punch and simplify, you are going to have your charge as 1.8 times 10 to the negative 4 coulombs. That is cure B. Maybe if you're also asked to find cure A, you can also take that, okay, cure A plus cure B is cure. It means cure A is also cure minus cure B. Alright, and then now like we replaced here, and then you take your cure 3 times 10 to the minus 4 minus 1.8 times 10 to the minus 4, and that will give you a response. Alright, so like I said guys, we are in this together. Make sure you punch and you give me your answer. Thank you guys for watching. I hope you enjoyed the video. If you love the video, make sure you like the video, you share the video with your friends, and you subscribe to the channel, because in subsequent videos I'm going to be uploading more and more on physics solutions for Northwest Mock, Southwest Mock, and also the GCE. So guys, see you in the next video.